All right, let's talk about the one topic that comes up in pretty much every single coding interview: time and space complexity. If you're prepping, you know you have to nail this. So today, we're going to break it all down into a super simple cheat sheet to get you ready.
So, you've written this amazing piece of code, but how do you actually know how fast it is? I mean, you could put a timer on it, right? But that's not really going to work. It all depends on your computer, what language you're using, even the data you test it with. What we need is a consistent, universal way to talk about how an algorithm performs as its input gets bigger and bigger. And here's the best part: you do not need some advanced degree to figure this out. Seriously, it all comes down to just 8 and only 8 fundamental growth rates. If you can get these down, you'll be able to analyze pretty much any algorithm they throw at you in an interview.
Okay, before we start throwing around a bunch of notation and letters, let's just build a little intuition. We need to get a feel for what fast and slow actually mean when we're talking about code that needs to scale up. This slide just lays it out perfectly. On one side, you've got logarithmic growth. Think about finding a name in a phone book. You don't start at page 1, right? You jump to the middle, figure out which half the name is in, and then you literally throw the other half away. You're cutting the problem in half every single step. It is ridiculously efficient. And then you've got its evil twin on the right, exponential growth. Here, the work doubles with every step. This scales so horribly that it's basically useless for anything but the tiniest sets of data.
All right, so now that we can kind of feel the difference, let's learn how to talk about it like a pro. This is where the formal language comes in, and the one you're going to hear all the time is Big O. Think of Big O as a promise. It tells you the absolute worst case scenario. So when we say an algorithm is O of n, and n is just the size of your input, we're making a guarantee. We're saying its performance will never be worse than growing in a straight line with the input. It's the performance ceiling. Big theta, on the other hand, is a little more specific. It gives us what's called a tight bound. If something is theta n, it doesn't just grow no worse than linear, it grows exactly linear on average. So real simple. Big O is the ceiling. It won't get worse than this. Big theta is the whole hallway. It's stuck between a floor and a ceiling. Okay, time for the main event. We're diving into the cheat sheet itself. We're going to walk through the 8 most common complexities you absolutely have to know, starting from the best and going all the way down to the worst. First up is the absolute gold standard, O1, or constant time. This just means the operation takes the exact same amount of time no matter how huge the input is. Think about grabbing an item from an array using its index. Doesn't matter if the array has 10 items or 10 million. Nope, it's instant. This is what we're always hoping for. Next up is O of log n, logarithmic time. This is our phone book magic trick. Every step we take, we slash the amount of work in half. You have no idea how powerful this is. To find one item out of a billion, it would only take you about 30 little steps. That's efficiency right there. Now, you're going to see this one all the time, ON, or linear time. And you know what? It's perfectly fine. It just means that if the input doubles, the work doubles. It's a straight line, like looking for something in a messy room. You just have to check every single spot one by one. This next one is really cool, O of n log n. This is famous in the computer science world because it's been mathematically proven to be the absolute best you can do for sorting things, assuming you have to compare elements to each other. All the famous sorting algorithms like merge sort and heap sort, they live right here. And here's where things start to get a little scary. We're now on O of n squared, or quadratic time. You usually see this when you have a loop running inside of another loop. And performance gets bad fast. If your input size is just 10,000, you're suddenly looking at 100 million operations. Your program is starting to sweat. Okay, we've left the danger zone and we've basically walked right off a cliff. Welcome to O to the n exponential time. With this one, for every single new item you add, the work doubles. This is that staircase we talked about. Algorithms like this become totally useless for anything but the tiniest inputs. And finally, if you thought exponential was bad, meet O of n, factorial time. This is the stuff of nightmares. This is pure brute force, like trying every single possible route a traveling salesman could take. It's only possible for a tiny, tiny handful of inputs before it just breaks. Okay, so now you've got the building blocks.
But just knowing the definitions isn't enough. What's really going to make you stand out in an interview is knowing about the common traps and the little details. Let's get into some pro-level insights. You'll hear this all the time. It's one of the biggest oversimplifications in programming. People just say, oh, hash maps? Yeah, that's constant time, O of 1. But here's the real story. On an average day, yeah, they're O of 1. But in the absolute worst case scenario, they're O of n. How? Well, hash collisions. If you get super unlucky and every single one of your keys hashes to the same spot, your fancy hash map basically just turns into a plain old list, and you're stuck searching through it one by one. Here's another classic you'll hear: Quicksort. It's one of the most famous algorithms out there, and everybody just knows it's O(n) log n. And again, it's a little more complicated. Its average case is fantastic. It's theta of n log n. But Quicksort has an Achilles heel. If you keep picking bad pivots, like, say, the smallest element over and over again, the performance totally falls apart and becomes a slow, quadratic theta n square. So all this theory is great, but how do you actually turn it into a job offer? Let's put together your playbook for the interview. Okay, when the interviewer asks you about the complexity of your code, and they will, here's your 3-step plan to knock it out of the park. First, always state both time and space complexity. Don't forget space. Second, show them you get the details by talking about the best, average, and worst cases. And third, if you used recursion, you have to talk about the space it takes up on the call stack. That shows a really deep level of understanding. And that's a wrap, but you're not done yet. Here is your challenge. Go find 3 coding problems online, but before you write a single line of code, just stop. Analyze the problem and figure out the time and space complexity of the best solution you can come up with. If you practice doing this, it'll stop being theory and it'll become an instinct.